In this module, we are going to study the very important Taylor's theorem. Recall our definition of derivatives interpreted in terms of linear approximations. Suppose f is differentiable at the point x, then f of x plus h is equal to f of x plus f prime of x at h plus an error term. And this error term has the property that limit h going to 0 of the error term divided by h is equal to 0. So this approximation is a reasonable one, a reasonably good approximation. The question naturally arises, can we make a better approximation if we know not only that f is differentiable at the point x, but f is k times differentiable at the point x? So let's see what happens. Suppose f is k times differentiable at x. Now, one would like to have an approximation of f of x plus h in terms of the data that you have about f at the point x. So can we approximate f of x plus h in terms of f at x? So we can do an approximation because k times differentiable automatically means it's once differentiable, and we have this approximation. Of course, the goal is to do much better than this by using the higher derivatives. Now what will be our guess? We have approximated f of x plus h using something that is linear. So the natural thing to do would be to try to approximate f of x plus h using a polynomial. Let's try to do that. Can we approximate f of x plus h using a polynomial? Now what polynomial would you choose? Note that the polynomial that we have considered before is f of x plus f prime of x times h. This is a linear polynomial, a polynomial of degree 1. Not only is it a polynomial of degree 1, it's a special polynomial. So note this is treated as a polynomial in h. Of course, it's not a polynomial in x. X has been fixed. Note that this polynomial as a function of h agrees with f of x plus h treated again as a function of h at h equal to 0. Well, yes, when you substitute h equal to 0, this term vanishes. You get f of x equal to f of x. But p prime of h is also equal to f prime of x, right? Because when you differentiate this with respect to h, this f of x term vanishes, and f prime x h, the derivative is just f prime x. So this function p of h agrees with f of x up to order 1 at x, or rather, to write it more precisely, agrees with f of x plus h up to order 1 up to order 1 at h equal to 0. Okay. Now we want to produce a polynomial that agrees with f at the point h equal to 0, not just till order 1 but till order k or k plus 1 or whatnot. Here we are assuming f is k times differentiable, so up till order k. Okay, so how would you do that? What we want is a polynomial p of h with the property that p of 0 is f of x, p prime of 0 is f prime of x, dot dot dot, p kth derivative at 0, we want it to be the f kth derivative at x. Okay. Now, if you think about this for a moment, you will soon understand that it might be a good idea to use these special monomials of the form h bar r, 0 less than r less than k, right? Look at these special monomials h bar r. Look at the derivative. The derivative of this is r h bar r minus 1. Okay, so these h bar r have the special feature that rth derivative is r factorial and all other derivatives are 0. All other derivatives are 0. Of course, I am treating it as a function of h and differentiating with respect to h. So, if you consider h bar r by r factorial times the rth derivative at x, if you look at this term, differentiate r times, we get well fr of x, right? Because the rth derivative of hr would be nothing but r factorial, which will get cancelled with the r factorial in the denominator, and you are left with frx. So this prompts us to consider this polynomial p of h, which is defined to be f of x plus f prime of x h plus f2x by 2 factorial h squared plus dot 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 f kth derivative of x by k factorial times h bar k. Okay, and this is called the kth order Taylor polynomial of f at x. Okay, now is p of h a good approximation of f of x plus h? The following theorem answers this question. Theorem: let f from AB to R be k times differentiable in AB and x comma x plus h closed interval, let it be a subset of AB. Then 1, P approximates f to order k at x. What does this mean? This means if you define r of h to be f of x plus h minus p of h, then limit as h approaches 0, r of h by h bar k converges to 0. Okay, so this just says that the remainder term f of x plus h minus p of h gets really small as h goes to 0, and this is quantified by saying it approximates to order k. R of h by h power k itself goes to 0, not just R of h by h as what happened in the definition of the derivative. Number two, if q is another polynomial of degree less than or equal to k, such that q approximates f to order k at x, then q is equal to p. Right? That means there is only a unique polynomial which has the feature that that polynomial approximates f till order k. And third, if we assume f is k plus 1 times differentiable in AB, then R of h, you can write it as f of k plus 1 of theta divided by k plus 1 factorial times h power k plus 1. You can write an explicit expression for R of h. Let me immediately make a remark. This is known as Lagrange form of remainder, and it is very useful. It's very useful in the following sense. Suppose we know that mod f of k plus 1 theta is strictly less than or equal to m for all theta in AB. For instance, we know this for sine and cosine. We know that the derivative of sine is cosine and the derivative of cosine is minus sine, and these just get repeated. The higher order derivatives just get repeated. So we know that if you are considering the sine function, no matter what derivative you take, it's always going to be modulus less than or equal to 1. Right? So in many functions, we do know such data about any derivative. So we have this mod f of k plus 1 theta is less than or equal to m when theta comes from AB. So modulus of R of h is going to be less than or equal to m by k plus 1 factorial times mod h power k plus 1. Now observe that in the Lagrange form of the remainder, there is a quantity theta that is unknown to us. This theta will in general change when you perturb the point h. So even if you have fixed x, depending on the h, this theta will change. So this remainder form, this remainder term, even though I have written R of h, this expression on the right, there is an implicit dependence of h even in theta. So a better way to write it is to write this as theta of h. And this theta of h function is sort of unknown to us, how it behaves. Whereas in this expression, that additional dependence on h has disappeared. The dependence on h is solely coming from this. A function that we understand really well, mod h power k plus 1 is a very simple function. Okay, so the additional dependence on this function theta, which is in general unknown, is gone. So this Lagrange form of the remainder, when you know you have some estimate on the derivatives, is very, very useful. And this will be illustrated throughout in the coming modules when we talk about the elementary functions, sine, cosine, and so on, defined in terms of power series. Okay, on to the proof. Well, let's start with the first part. Let's first start with the first part. We already know that r of h and its first k derivatives are 0 at h equal to 0. Okay, and r is k times differentiable in AB. Okay, in the closed interval AB, not in the closed interval AB, sorry, in the closed interval x plus h. Okay, so we can apply mean value theorem to R in not x plus h, I am in 0h. We can apply mean value theorem to R in 0h. What do we get? Well, R of h minus R of 0, which is 0, is going to be sum R prime of theta 1 times h. Okay, for convenience I am assuming h is greater than 0. I am assuming h is greater than 0 because I am writing 0h. Whatever I am about to write, if h is less than 0, you just have to apply it to minus h0. You will just have to apply an analogous argument to minus h0. For convenience, I am assuming h is greater than 0. Okay, so r of h minus r of 0 is r prime theta 1 times h by mean value theorem, where theta 1 lies in 0h, or rather the open interval 0h. Open interval 0h. Now we can of course apply the mean value theorem again to the function r prime of theta 1 minus 0. Look at r prime of theta 1 minus 0. Well, this is just r prime at 0, right? So you can apply the mean value theorem again now to the function r prime to get r double prime of theta 2 times h, where theta 2 lies in 0 theta 1, right? So this is just applying the mean value theorem again. Now note, we know that the function r is k times differentiable in the closed interval 0h. But we cannot apply the mean value theorem k times on this closed interval simply because we do not know whether kth derivative of r is continuous in closed interval 0h. That is unknown to us, because we are just assuming kth order differentiability of the function f in the open interval AB. So we cannot apply the mean value theorem k times, but we can apply it k minus 1 times. Okay, so applying mean value theorem k minus 1 times, we get r of h is equal to r k minus 1 of theta k minus 1 times theta k minus 2, theta k minus 3 theta 1 times h, where we have 0 less than theta k minus 1 is less than theta k minus 2 is less than is less than theta 1 is less than h. Okay, so this is by repeatedly applying the mean value theorem. Now the quantity we are interested in is r of h by h bar k. Okay, and this just turns out to be r of k minus 1 times theta k minus 1, theta k minus 2 theta 1 h by h bar k. Okay, now how is this going to be, how are we going to simplify this? Well, observe that these theta k minus 1, theta k minus 2 are all less than h, So this whole thing I can write it as r k minus 1 times theta k minus 1 and cancel off h and this, and cancel off all of these also. So what I'm doing is in the numerator I have a quantity which is less than the denominator. So I'm going to replace these essentially by h bar k minus 2, right, and cancel it off. So this is strictly less than r k minus 1 by theta k minus 1 by h. Okay. Now what I am going to do is I am going to be clever. The denominator I am going to replace by a smaller quantity and write this is less than r k minus 1 theta k minus 1 divided by theta k minus 1. Right? Which I can do. Okay. Now as h goes to 0, well, theta k minus 1 also goes to 0. We don't know how it goes to 0, but it certainly is going to go to 0, right? That means limit h going to 0 of r k minus 1 theta k minus 1 by theta k minus 1 just converges to 0 because this is just rk at 0, right? So what happens is the quotient goes to rk plus 0, which is 0. We know that because that's how the function r was defined. We had defined the function p to agree with function f till order k at the point h equal to 0. Okay, so this concludes the proof. This concludes proof of part 1. Okay. Part 2 is easy. Is easy and left to you. Now let's go to part 3. In this part, let me recall, we are assuming that f is k plus 1 times differentiable at or in AB. And we want to get an explicit form for R of h. Explicit form we want. Okay, so now we already know that R of h is just f of x plus h minus p of h. Okay, now what I'm going to do is I'm going to treat R as a function of u for a moment, because at the end of the day, even though I write R of h, sort of h is fixed, right? So I'm going to treat it as f of x plus u minus p of u. Okay. Now, what I plan to do is look at f of x plus u minus p of u. I want to apply Rolle's theorem to R of u in 0h. I want to apply Rolle's theorem to R of u in 0h. But can I apply Rolle's theorem to R of u in 0h? No. So even though R of 0 is 0, we don't know whether R of h is 0. Is this 0? Well, that's not clear. So what we do is we consider this new function g of u, which is just going to be f of x plus u minus p of u minus something to make the value at h 0. But if I make the value at h 0, I will be modifying these first few terms at the point u equal to 0 also. If I want to make this g of u 0 at u equal to h, I don't want to touch the value of g at the point 0. So what I do is I subtract a quantity lambda. Lambda is going to be a constant which I am going to determine times u par k plus 1. Why did I do u par k plus 1? Because of the convenient property that at u equal to 0, the first k derivatives vanish. At u equal to 0. So this modification to the function r that I am doing by subtracting lambda u par k plus 1 does not affect the behavior of the first k derivatives at the origin. Okay, that's the logic behind subtracting lambda u par k plus 1. Okay, Now, how do we determine what this lambda is? Well, simple. Differentiate k plus 1 times at x equal to h. Okay. Or rather, you don't have to do all that. Sorry about that. You don't have to do that at least now. You just want to determine what lambda is. Well, we want f of x plus h minus p of h minus lambda h bar k plus 1 to be 0, right? So that just gives lambda is going to be f of x plus h minus p of h by u bar k plus 1. Okay, this is not u bar k plus 1, h bar k plus 1. Okay, now it really doesn't matter what exactly lambda is. I'm just telling you that there is a lambda that will make Rolle's theorem applicable to the function g. Okay, now observe the way we have done. G of 0 equal to g prime of 0 is equal to dot 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 is equal to gk of 0 is equal to 0. Okay, we know this, and we also know that g of h is 0. That's all we know. Okay, now applying Rolle's theorem, we get a point theta 1. Again, I'm going to assume that h is greater than 0 for convenience. Analogous arguments will hold when h is less than 0. There is a theta 1 in 0h, in open interval 0h, such that g prime of theta 1 is 0. Okay. Similarly, applying Rolle's theorem again to 0 theta 1, we will be able to conclude that g double prime of theta 2 is 0, where theta 2 comes from 0 theta 1. Okay. When you apply this repeatedly, what will happen is we will get all the way till we'll get a point theta k such that this will be somewhere in 0h, such that gk of theta k is 0, right? But we are now assuming that the function f is k plus 1 times differentiable. So we can apply Rolle's theorem once more. To get a point theta k plus 1 in 0 theta k, such that g of k plus 1 theta k plus 1 is 0. Okay. Now this is what I want. Well, how is this useful? So we have f of x plus h minus p of h minus lambda. Sorry, we don't have that. Sorry about that. We have g of u is f of x plus u minus p of u minus lambda u bar k plus 1. Okay. What will be the k plus 1th derivative? K plus 1th derivative of this at theta k plus 1? Well, that's just going to be f of k plus 1 x plus theta k plus 1. This polynomial is a polynomial of degree k, so that vanishes, and this will just give us minus k plus 1 factorial times lambda. Okay. In other words, lambda is just going to be f of k plus 1 x plus theta k plus 1 divided by k plus 1 factorial. This is what lambda is going to be. But wait a second. How was lambda chosen? Lambda was chosen so that f of x plus h minus p of h minus lambda h bar k plus 1 is 0. Right? In other words, lambda h bar k plus 1 is what we have been calling r of h all along. It was just a different name that we have given. Right? But lambda is nothing but f of k plus 1 x plus theta k plus 1 by k plus 1 factorial. By k plus 1 factorial. Right? That's what we have concluded by repeated application of Rolle's theorem. That means this into h bar k plus 1 is r of h. Is r of h. And if you look carefully, this is what we wanted. This is what we wanted. This is the Lagrange form. Okay. So I hope the proof is clear and what is going on and the logic behind the proof. So it's easy to understand this proof. It's not that hard, but the logic behind the proof is what I want you to appreciate. So please go through this proof once more and try to make sure that you digest it completely. We will anyway revisit Taylor's theorem once again after we study integration and give a different form of the remainder term. This is a course on real analysis and you have just watched the module on Taylor's theorem with Lagrange form of the remainder.